Well, hello, everybody, and welcome to our second evening of TWSS 2021. I want to thank everybody for joining us tonight. We have had such a good series of talks. It's been a really good event so far. And I'm super excited to introduce to you Dr. Daniel Main. Daniel is one of our application engineers, and he's my plasma expert in so many ways with my any clients that are looking into stuff, any plasma simulation. So a little background on Daniel is he earned his PhD in computational plasma physics at CU Boulder in 2006. Since then, Daniel has worked with a variety of plasma models, including direct Vlasov integration schemes, implicit schemes, hybrid models, which include fluid electrons and kinetic ions, standard pick methods, and Eulerian and Lagrangian fluid models. Dr. Main has worked at Los Alamos National Lab and the Air Force Research Lab, performing work related to magnetospheric and ionospheric physics. Dr. Main currently works at TechX Corporation as an application engineer, where he helps support customers using VSim and USim, as well as adding to the capabilities of both software packages. As part of his work at TechX, Dr. Main has Air Force contracts, which involve the use of USim and VSim to model electromagnetic propagation through dense plasmas. So on that note, Daniel, I think you can go ahead and begin.
All righty. Well, thanks for that introduction. Can you guys hear me? Can you hear me okay?
Yep, you sound great.
Okay. So today I'm going to be talking about what probably a lesser known feature of VSim. It is part of the visual, and I want to show you how to get to it and use this capability because it's really a fantastic capability. I'll give you the background, some background papers on where you can learn more about it. And so these are my colleagues. We're doing experimental work at CU Boulder. So Mark Olkowski is leading up that effort, and BJ Harrod is doing the theoretical effort. Mark also does some of the theory also. And then these are some of their students also at CU Denver. So just to get started, broadly speaking, or narrowly speaking, I guess, one application would be the communication blackout problem that we're investigating, although we're thinking about the problem a little more broadly than just that, but this is one of the applications. And of course, this is a very well-known problem since the beginning of the space shuttle back in the 60s, and probably even before they knew about it. So essentially, the problem is that if let me see if I can. If the electromagnetic dispersion in an unmagnetized plasma is given by this equation here, and so if we just simply solve for the wave vector k, it's pretty easy to see that in order to get real solutions, that is, in order for the wave to propagate through the plasma, the electromagnetic wave has to have a frequency greater than the plasma frequency. Now, a few caveats of this derivation is it assumes a plane wave solution. And so one of the questions that we could ask is there an advantage to other antenna designs? So a plane wave solution would be something along the lines of an electric dipole. And so are there other types of antennas that might perform better or might not suffer such a large loss? And then another question that we address is what role do collisions play, which we can't really see where collisions fit into this simple scheme. And so I'll introduce a more sophisticated model in a bit, or a more sophisticated theoretical framework for investigating how collisions, or what collisions might do. By collisions, I mean typically just your, of course, any collision, but I'm just mainly thinking of collisions between electrons and neutrals in this context. Before we get started with where VSim fits into this problem, I want to introduce USim. And so we started our investigation using USim, which is our finite volume time domain fluid model. And USim can be used to model many different types of problems. Jared gave his talk this morning on the new capabilities in VSim with fluid, which is absolutely fantastic. I'm glad to see that we're starting to do some of that hybrid modeling within VSim, particularly things where you're mainly just interested in the ion dynamics, or some people are actually also interested in neutral dynamics. But there's the electrons sort of then play a secondary role in just generating neutrals through various collisions. So, so his framework would be sort of fit into this multi-fluid approach with Ohm's law. So you solve for the electric field using Ohm's law, and of course we can do that in USim. We can also do a fully magnetized charged fluid evolution coupled with Maxwell's equations. You still get an advantage using a fluid model there because we don't have to resolve the Debye length, but there is a severe time restriction at when you couple in the full Maxwell's equations in any fluid model, unless it's implicit. We also have MHD models. We can evolve the Navier-Stokes equation, and then a really neat capability actually within USim is within the MHD framework, which is a single fluid approach. We can have multiple species through the rate equations. That is, the total density is evolved, the total pressure, but then there could be components to that fluid, which we call a multi-species single fluid model. And that's actually what we used for modeling this hypersonic vehicle problem. And so this is a standard problem that comes with USim. If you're interested in USim and you get trial license, then there's several of these hypersonic vehicle examples that are set up for you already. And so we ran that simulation, and then this was the RAM C problem that's been around since the 70s, and there's not a lot of experimental data out there to use. And so these are just some of the standard problems, and the RAM C is one of the standard problems. And then, so this here, we're showing you the evolved electron density. I don't remember all the details of the setup. It had some Mach. I think it was, I don't remember off the top of my head, certainly greater than Mach 5, which is sort of the standard beginning of a hypersonic flight. And then, so this is the density. We see the peak density is around 4 times 10 to the 19 per meter cubed. So it's a fairly dense plasma. It would be very difficult to model this kinetically using explicit codes. And so we're using this USim. And then what I did, and you'll probably learn more about how to do this tomorrow with Tom's talk, and because he's going to talk about advanced using VSit to look at the data in more detail, like not VSit through VSim, but just VSit as a standalone product. And so I imported this data into VSit. I took a line out, which is the black curve here. I saved it as a text file, and then I read it in a Python, and I fit the data. And this is sort of the profile along this line of the electron density. So I thought that was really handy to be able to do that in VSit. And the nice thing about VSit is it just imports all sorts of data files, including the standard H5 data sets. So we find that the thickness is between 5 to 10 centimeters. I mean, this profile here shows it's around the flat top for about 4 centimeters, and then it decays as a Gaussian out to about 8 centimeters. The temperature, it's a cold, it's about 1 eV. So this is a cold, I would qualify this as a cold dense plasma. So we simplified this cutout just by assuming a constant thickness. And the reason that we're doing that is for theory. It's easier to compare with analytic theory, so the results with analytic theory. Of course, I could put in this more realistic profile if I chose to. And there's even a way to import the data directly. So there's all sorts of methods for getting the USim data into VSim. So for now, we're just doing a very simple fit, but there's more sophisticated methods if you chose to do that also. So we're using this linear plasma dielectric model, which is a standard part of VSim. You need either an MD or a electromagnetic package to use the linear plasma dielectric model. It was developed by David Smith back in 2007. There's a nice paper on it, which is really quite friendly and easy to follow and explains quite a bit of the details, even the computational methods used. And the nice thing about this scheme is, well, it's implicit. And the main reason that it's implicit is so that we can look at cutoffs and resonances. So the problem is that that if you try to look at cutoffs and resonance in a in an explicit scheme, you actually end up getting numerical instabilities. So by going to an implicit method, you can get around those numerical instabilities. It has an added benefit that for very dense plasmas, we're not there in my problems that I'll be showing you, but for very dense plasmas, sometimes the density is so large that the time step restriction is actually greater than the Courant condition. And so this scheme avoids that. You can use a time step bigger than this, but you still have to satisfy the Courant condition. That is, you have to have your cell size small enough, or your time step small enough that light waves don't pass through a cell in less than one time step. Okay. So just briefly, a few things about this. It's frequency dependent. So that is, it converts the cold magnetized linear dielectric tensor into time derivatives, and then it solves Maxwell's equations. And in order to do that, this scheme introduces these linear RF currents, and that's J sub S here. And in doing so, we nicely introduce this collisional term, nu sub S, which can serve three purposes. You can actually use it to model real physical collisions, which I've used that for that. You can put in some form of heuristic warm broadening. I have not used it for that, but you can also use it to put in absorbing boundary conditions. So, which is a very nice feature when you're looking at electromagnetic propagation in a finite size simulation domain. Okay, if you choose to use this, remember that this is a linear model, so wave amplitudes are assumed to be small. For practical purposes, this means that if you try to put in a large RF signal, you'll probably get very strange looking answers that I would not believe. And the reason is because there's no nonlinear saturation mechanisms to keep the large waves in check. So any linear growth is unphysical. I mean, it happens for a short time period, but typically it saturates in some nonlinear mechanism. So linear growth cannot continue forever. And that's linear meaning exponential growth. And so this model does not include that sort of physics. So just make sure that your RF signals are small to keep the results believable. Another important feature is that the Mao boundary conditions have a different implementation than the standard method. And starting in VSim 12, we'll have the correct implementation in the visual setup. For now, you'd have to do the Mao treatment. MALs are mass absorbing layers in the text-based, and I'll show you that what I mean by that in just a minute. And I've never used the Sheath model, but there is a Sheath model that you can implement in this. So by Sheath, I mean, you know, small scale to bi-scale structures that form near boundaries and surfaces. Okay, so what I want to show you then is where and how to access this in the visual setup. So this is, you know, your standard VSim or composer interface. This is actually probably, let me see if I have. This is VSim 11 that we have out now, 11.0.1. And if you want to include the plasma dielectric model, then you just need to make sure that your field solver is set to electromagnetic. And then, you know, some of you guys may have used this for a long time and not even known it was there, or you saw it and you weren't sure what it was. So you right click here and you add plasma dielectric, and it's that simple. And then you get this new. So if I just click that, then there it is right there. And then once you add it, you can right click here and you can add an ion species if you want. And so it's as simple as that. It's a new field solver right there. By new, I mean it's invoking a frequency dependent dielectric within the simulation domain. Now the default would be for the dielectric to fill the whole region. Typically you wouldn't want to do that. So what you do is you put in a density profile right here, which could just be your space-time function. So in my case, my density profile is just these Heaviside step functions that go between you know, x1 and x2, z1 and z2, and for some reason I called it y lower and y upper. But so in my case, it's just this rectangular box, 3D volume within the simulation domain. So that's how you could put in a spatial dependence. You could also use the same spatial profile for a frequency term. So I didn't do that in this particular simulation, but I did it for in the past. And so you would put in a, you know, a spatially dependent, same density profile, but it would, you know, multiplied by some collision constant. Okay. So all right. Now, another really handy feature that I enjoy immensely is the ability to just put in antennas within using Composer. And I'll go back to what we were just looking at in just a minute, how to do that. So I really love that you can just put in sort of an arbitrarily shaped antenna, subject, of course, to the grid resolution. So if you have a, you know, my grid size is 1 millimeter, so I'm never going to resolve features smaller than 1 millimeter. That's a pretty small antenna, but I'll explain why it's so small in just a minute. But just to go back to that, let me actually use a different all right, so here's a different setup. Well, it's similar setup, but so in my case, actually, what I did was I created a square loop antenna. You know, that's kind of odd, but in rectangular coordinates, that's as good as you can do. And because I'm resolving this at the grid scale, so that's a cell right there. So each tidbit of current density going through my antenna is 1 cell thick. So I actually have, here's my loop antenna in 3D rectangular coordinate system. It's an octagon. So it goes up and then it diagonally goes over, goes to the right, diagonally goes down. So there you have it. Now, if it was a bigger antenna, I could involve more cells and I could get closer to having a real loop. You know, if I had a 16-sided loop, if it was a larger antenna, then I could parameterize a space-time function, and you could then have 16 different individual current densities mimicking as closely as possible a circle in a Cartesian geometry. So the way you do that, of course, you just right-click here, and then you add a current distribution, and then it's this general distributed current. So I've got 8 of these general distributed currents, and then I have space-time functions. So JZ, for example, is I have some ramp-up function so that it doesn't just turn on too abruptly and cause ripples, unphysical ripples. And then this is just a single frequency source, so it's just sine of omega t times my amplitude. And the corner pieces, so there's my corner piece right there. Now there's a JY and a JZ component in order to get the corner. Now you may wonder, am I doing it right? Did I get the right directions and all that? So what I like to do is put in histories in order to provide sanity checks. So I put a history right here, and it measures the current density in this cell. Same with this history and this history. So these two histories should be equal in magnitude but opposite in direction. And lo and behold, I already plotted the data, so I didn't have to go through plotting it. But you could go to your Visualize tab, and you could go down to History. You open a History tab, and then plot the two currents, and you can see that they are going in the opposite direction with equal magnitude. So I seem to have set up those two current sources correctly. And of course, you could do the same for all the current sources to make sure they are turning on and correctly and operating the way we expect. Okay, so I can also show you what the plasma dielectric looks like. So this is a 3D simulation. This actually, let me make sure. Hold on. So my plasma density is, in this particular simulation, actually, I did not include the plasma. Okay, so you could, if these simulations had the plasma dielectric in it, then you would just go to data overview and then plot the density of the plasma dielectric. Okay. Alrighty, so I just wanted to show you some of these neat ways of kind of navigating around in the visual setup as you set up your problem. And if I'm speaking to the choir, sorry about that, but I use VSim a lot, so it's and everyone kind of comes up with their own workflow. But okay, so for this problem, I chose to model this loop antenna as this square antenna, and it is meant to mimic a magnetic dipole. So what we're going to look at is the wave propagation through this dense plasma from two different sources. Actually, in this part of the work, I did two different size loop antennas, and then I did a plane wave. So here is just a two-dimensional plot cut through in the middle of the simulation domain. And here's my antenna. So this is the current density. So the current density is going to the left and down, to the right and up. And then of course, later time, because it's a function of time, everything flips. this is my plasma sheath. It's 5 centimeters thick. And then I also put in a bunch of diagnostics. So for example, along this line in the middle, I collected the electric and the magnetic field at every single time step. Now, another neat thing about VSim 11, actually, is you can see some of the history when you create them. So this, for example, is an attempt at creating a far field box. I say attempt because I think I set it up right. My box simulation isn't big enough actually to compute the far field correctly. But nevertheless, there's my far field box. And then these are, for example, here's my, where I'm collecting the magnetic field, and then here's where I'm collecting the electric field at every single time step. So it's nice that now you can visualize the history to see where the data is being collected. Okay, and then this is a plane wave. So this actually should go all the way to the boundaries. I learned after doing some of these simulations, I get a lot of edge effects. So this is my plane wave, but with edge effects, I ended up not really creating a plane wave. So I needed to extend the plane wave antenna all the way to the boundaries and make it periodic, which is what I did. My plane wave solution of my plane wave simulation. And then all simulations in these runs are 3-dimensional. I drove them at a gigahertz. So I was just looking at a single frequency in these runs. For the plane wave, I just drove a current in the X direction, and that launched a wave that went in both up and down directions. So then what I did was, so basically for each antenna, I did 2 runs, a run with the dielectric and a run without the dielectric. And then I would compute the root mean square at a given point, at Y naught here, in some point above the dielectric, so like 8 centimeters, or actually at 9 centimeters. And then, sorry, let me take a step back. I collected data in a plane, but I didn't really end up using that data too much. So what I really did was I collected data. What I really cared about was that data along the line through the center. And that was taken at x max over 2 as a function of y and z max over 2. And then this had also, right, and I summed over time. And I computed the root mean square as a function of y. So then I just defined this transmittance as the root mean square with the dielectric divided by the root mean square without the dielectric. So that's what these quantities are here. So this is, all of these quantities sort of compute the loss. Because my colleagues at CU Denver are electrical engineers, they think in terms of the dB, the decibels. So I kind of use this formula here to convert them into decibels. And so this, for example, was a run with 3 different antennas, with the plane wave antenna, and then the small loop antenna, and then the large loop antenna at 1 gigahertz. And we see a pretty big difference between the small loop antenna, which is the blue curve, and the plane wave. At this frequency, there's a lot more loss in the plane wave. So we are in fact seeing an improvement compared with the, we're seeing an improvement with the loop antenna. Now, don't get me wrong, this is still 95 dB. So this is still a lot of loss. So I'm not pretending to say that we're transmitting the signal, but there's less of a loss. Okay. So with all these plots, by the way, if you're not used to dB, which is not my favorite unit, but some people use it a lot. So smaller number means less loss here because of this, basically because of this negative sign. Okay. Now I did a run where I added collisions. So these are collisions between electrons and neutrals. They're just your typical momentum conservation collisions, I would say, considering how cold it is. There's not really, the ionization of the air, by the way, isn't due to because of plasma sod. It's only 1 eV. It's due to the ram pressure and the speed of the vehicle. And so that's what causes the ionization of the air around the vehicle. Okay, so again, we see an improvement with, so let's see, so let me make sure I'm looking at the right stuff here. So the collision frequency here was about 2 times the plasma frequency. So I forget what the density was, but I played around with densities that were around neutral densities of around 10 to the 22 to 10 to the 23 per cubic centimeter. Sorry, per cubic meter. So an atmosphere is, I forget off the top of my head, but we're looking at like anywhere from 1/100 to 1,000th of an atmosphere. So 1% to 0.1% of an atmosphere, roughly speaking, maybe in that ballpark. And so we're not talking about huge collisions then, in terms of what the density requirements are of the neutral to see a pretty big improvement in what you in transmittance. So so if we go back to this curve, the plane wave was at like 125 dB, and now it's jumped down to like 60 dB. So a big improvement by introducing collisions into the plasma dielectric. Okay, and then one part of this work is putting small cracks or dips in the sheath that surrounds the vehicle. How those form is sort of up for debate exactly. We do see some plumes that form in the modeling, and within those plumes you can see density dips. And what's really neat, I am not showing any field data here, but even very small, we're looking at a 30 centimeter wavelength with this electromagnetic wave because it's a 1 gigahertz. And this gap was only 1 centimeter wide, and you still see leakage. You can still see signals that go through such small gaps. So if we go back to, let's just use the plane wave here. So you're looking at 30 dB loss with a very small gap. So the density dip was 0.1% of the ambient plasma. So without any dip, without any collisions, the loss was 125 dB. And with the dip for the plane wave, you're down to 30. So that's a huge improvement in the amount of signal that's transmitted. So here, I'm comparing just the plane wave. So this is with no collisions, no dip. And then now all the way down here, this is with collisions. So a 60 dB gain, and then another 20 dB. This did not have collisions in it, it just had the dip. So we're basically looking for mechanisms that can improve transmittance. Okay. Okay, and then now this is what role collisions play. So the black curve is the plane wave. I'm sorry, all three curves are the plane waves, and then I looked at different levels of collisions. So if the collision frequency is 2 times the plasma frequency, then this is the gain in transmittance. But if it's only 0.2, you still see a gain, but of course less of 1. Okay, so now let me just provide a bit of explanation for this, for both looking at a magnetic dipole and for thinking about the role of collisions, neither of which to me are intuitively obvious. So if a year ago, if you had asked me what do collisions do in terms of transmittance, I would have shrugged my shoulders and I wouldn't have known. And I would have had no intuition. But there's actually some neat ways of thinking about it. And one way of thinking about the role that different types of the plane wave versus the magnetic dipole play is to think about this concept of wave impedance, which isn't necessarily what plasma physicists are trained to think about, but electrical engineers are. So it pays to work with a variety of different people with different ways of thinking about a problem. So this is work from V.J. Harrod at CU Denver. And he just did some simple modeling in this paper, this 2019 paper. He's one of our colleagues that we're working with currently. And he set up this simple model where you have this slab dielectric, and then you have an incident wave, you have a reflected wave, and you have a transmitted wave. And he did this and he came up with his transmittance equation here, which you need to read the paper. I don't know off the top of my head how to derive this, but it's all in paper. And the important thing that you get out of this equation is that Z sub W is the wave impedance. So for a plane wave, that's a constant. It's 120 pi ohms. So the wave impedance of a plane wave is a constant. It never changes. Z is the plasma impedance. And then, so the important thing in this equation is that Z sub W is different for a plane wave and a magnetic dipole antenna. And in fact, for a magnetic dipole antenna, it's frequency dependent. So whereas you can't get any improvement with the impedance matching with a plane wave, you can with a magnetic dipole. And this plot here shows the results of that. So this is the magnitude of the impedance, and this is frequency down here normalized to the plasma frequency. So 1 here would be perfect transmission. And so the black curve is the plane wave impedance. It's 120 pi ohms. And then the loop antenna impedance is here, and then the plasma impedance is the blue curve. And you can see, so when I look at this, my thought is you'll probably see more improvement at lower frequencies, because the impedance of the plasma and the plane wave are just drastically different, whereas the loop antenna and the plasma sort of follow each other. So that's what this simple theory shows. Now, we did some preliminary experiments, and so I'll come back to this in just a minute with some current work that I'm doing to look at how the transmittance changes with frequency. See if my intuition is right. Now, before moving on, we're in the process of setting up some plasma experiments at CU Denver to do some scattering experiments. But for the initial work, they use this special material to mimic the plasma, to sort of mimic some dielectric. Now, of course, this material is not frequency dependent, so that's the major way it differs from a real plasma. But nevertheless, so they this is the let's look at the 3-sheet case. So what they did was they had 2 antennas. One was a loop antenna. The other was a electric dipole antenna. So just a stick they sent the current through, and the other one was a loop that they sent the current through. And then they put the antenna in the middle, and they also placed it at the edge. So I'm just looking at the edge case where they placed 2 different antennas at the edge. And in this case, a bigger negative number is better. Let's see, make sure I get that. Sorry, a smaller negative number is worse transmittance here. So the orangish curve, sorry, I'm partially, I always have to apologize for this. I'm partially colorblind, and if I don't make the plots, I don't necessarily know what the colors are. But anyway, this curve here is the monopole antenna. So that's like the plane wave that we modeled. And then this curve here is the loop antenna, and we see better transmittance at certain frequencies for the loop antenna. So particularly here at around 1 gigahertz, and way up here, well, not way up, but around 2 gigahertz, we're seeing better transmittance. And then between, I would say they're about equal. So there is experimental evidence that, in fact, a loop antenna also behaves better or transmits better. Okay, so now, why would collisions help? So the way I think about it is the following. So the reason why a signal below, this is the way I think about the whole problem actually, just qualitatively. Why doesn't a signal that's below the plasma frequency get through? Well, the electrons can move fast enough to basically shield out any signal. That's just sort of my big picture, 3,000-foot overview of why this problem even exists. If you send in a signal and the electrons can respond fast enough to that signal, then it can shield out the electromagnetic wave. So if you dampen the electrons through collisions, then they can't respond as quickly, and you can improve the penetration. And that's sort of qualitatively why the electrons, or why including collisions, helps improve penetration of your signal. This is borne out through these Appleton-Hartree equations. So the wave vector, well, actually the index of refraction squared equals ck over omega squared, which is equal to this term on the right, where capital X is omega p squared over omega squared, and capital Z is the ratio of collision frequency to signal. Okay. So if you just play around with these equations, and K equals K real plus I times K imaginary, the skin depth is equal to 1 over K imaginary, the imaginary part of the wave number. So without collisions, Z is 0. If Z is 0, then K is purely imaginary. But with collisions, K becomes complex, the imaginary part goes down, and the skin depth increases. And if you don't see that, then just write these equations down and just start plugging in some numbers, and it'll pop up. That'll pop out pretty quickly. Okay, so that's sort of the theoretical role of collisions, and we plotted this. Actually, Mark Gurkowski plotted this. This is one of his plots, and this is a plot of omega over omega p. So this would be like your RF signal frequency on the vertical, and this is your collision frequency on the horizontal. and we are way down here. And this is plasma skin depth. So this is better, more penetration over here. This is less penetration down here. And you can see that as the collision frequency increases, the penetration depth increases. Okay. So I'm just going to skip through this because it's already 7:15. But in a nutshell, I went ahead and just solved the magnetic dipole equation that's in Jackson. And I just did the special case that the magnetic moment points in the x direction. And if you just go through and do all of the nice math, then you can write down this nice analytic expression for the hx. And of course, you could do the other two components just as easily. And this is what you get. And then I coded this up in Python, with remembering the convention that Jackson uses e to the negative I omega t for time varying sources. So in this equation, I set m equal to m naught e to the negative I omega t. And I solved this in Python. You could do this in any language you want. And my goal was to compare with my dipole moment, my dipole model in VSim. And in order to get a really good comparison, I had to switch to a 2D geometry in the RZ coordinate system. And so that actually is now a loop antenna that I am actually modeling a real loop antenna now, a real circle. And so here is the results. The blue curve is the analytic. The greenish curve is the VSim result. I'm just showing you this because I have included my MAO boundary conditions now. I find that those MAOs are extremely important. And here we go. They're working the way we would expect. So if I zoom in on the part that we care about, then this is what what the comparison looks like. So I would call this pretty good comparison. So I'm now actually modeling a magnetic dipole pretty well. And the way that I did it, again, was I excited an electric field in the phi direction. So remember, I'm 2D. So I'm just taking a cut in 2D. So the radius is 2.5 millimeters and the width is 1 millimeter. And I did a similar setup with in a Cartesian geometry using the exact same, using the same field solvers. But I switched to Cartesian coordinates and I launched an electric field in the x direction along the entire lower y boundary using periodic boundary conditions in the x direction. And there's what that wave looks like. So that looks pretty good. These are MAO boundary conditions up here. So you would expect there to be attenuation. Okay, so then I put in this sync hat function, which is a broadband signal over a wide frequency. And just real quickly, you can now pull this function up directly. It's one of the functions that can be used directly in VSim now. You don't have to write it in yourself. And this is what this signal looks like in the time domain. And then in the frequency domain, it's this nice flat signal. So this is time here, this is frequency here, nice flat signal. You can make these cutoffs more abrupt if you want, but you have to run it longer, and I didn't feel like doing that. So again, same method of collecting data. And then now after I collect the data, I take the Fourier transform of the time domain signal to get a frequency domain signal, and then I plotted the wave power, that is the Fourier transform, amplitude of the Fourier transform at each frequency with and without the dielectric. And this is what I get. So of course, this is the this is at 0.3 meters, so I'm well above the dielectric. The signal's gone through the dielectric for the black curve. This right here is the cutoff frequency. This is the plasma frequency. So this is without the plasma, of course, there's no attenuation, and this is with the plasma. And to get the transmittance, I just divide these two curves. So I did the same thing I did the same thing, but with the magnetic dipole. And strangely, I don't quite get, for some reason, I'm not entirely sure why, but I don't quite get a constant frequency like I do with the plane wave. It's very close to being constant, but I'm not entirely happy with that. So this is without the plasma, and then this is with the plasma. Again, I divide the two to get the transmittance. And the result is, this is the ratio. So this curve is, the blue curve is the ratio of the signal, of the dipole signal with the dielectric divided by the dipole signal without the dielectric at 0.3 meters. And then its black curve is the same thing, but with the plane wave. And we can see, in fact, that at lower frequencies, we see improved transmittance. So my intuition seems to be, my interpretation of that paper and theoretical result seems to be in line with this result. Okay, so these are the conclusions, and if you have any questions.
All right, thank you, Daniel. So there is a box, this is Q&A at the bottom of your screen. If you have questions, you can type them in there, and then Daniel can answer them for us. So I do have a few that were sent me separately, Daniel. So the first question says, how do collisions improve communication through a dense plasma?
So yeah, it's just, I guess by the way I think about it is with just that sort of the conceptual way, that is, the collisions sort of impede the motion of the electrons, and therefore they're not as responsive to the electric field. The other way is to think about it is through these sets of equations here, by increasing the skin depth of the wave when you include collisions.
What sorts of collisions do you think would dominate in this scenario?
Yeah, just your typical, like, just the momentum conservation type collisions between electrons and neutrals. Yeah, probably no sophisticated collisions, really simple collision model.
Right.
Here.
Is it possible to benchmark these results with a standard pick method?
Yeah, so that's actually one of my goals, is to just do a 1D simulation with pick, and then we would get we'd be using the Monte Carlo, a totally different collision model. So I would really enjoy that process of being able to benchmark two different models. And of course, another goal of this work overall is to also do the same thing with in a experimental plasma chamber. So that's what they're doing at CU Denver.
Let's see. Looks like, how is the skin depth resolved?
I mean, we don't really need to, I don't know if we really need to resolve the skin depth. We're not including any kinetic physics in this. So I don't know, I don't even know what the skin depth in this. I didn't go through to figure out, for example, what is what the skin depth is in this case. I mean, our grid size is 1 millimeter. So
let's see.
The model isn't really dependent on resolving the skin depth. So,
Right.
we're not really interested in the physics of that necessarily.
Do you get higher transmittance with plasma for some frequencies?
Yeah, for sure. If we just go back to this plot here, I know I went through these kind of fast, but this is sort of the transmittance here as a function of frequency. And so I sort of start believing my results here at around 0.2 gigahertz. And you can see that as we approach the plasma frequency, we get more signal through, and that by the time we get to the plasma frequency, you're at full transmittance. That is, the ratio is about 1.
Good question so far. Anyone else? I will say, so all of these talks are being recorded and they are all going to be on our YouTube channel, hopefully no later than the end of next week. We already have our keynote presentation up from yesterday from Maxine Lebuck, so you are welcome to go there. Also, if you do not have our most recent version of any of our software, VSim 11 or Sim 3, I would encourage all of you to go to the TechX website at txcorp.com, txcorp.com, and you can request an evaluation, even if you have a current license, but you don't have the most recent version. And then we can set up a new evaluation for you so you can see what's in the latest release. So another question, did you get a ratio larger than 1?
No, I didn't. And I'm very happy about that. That would be a very terrible thing. So this is, so we're seeing right here, the ratio sort of peaks at 1, which is where, of course, you expect above the plasma frequency, the ratio to be. So.
Okay. Any other questions? Also, we did make a slight change to our schedule for tomorrow. You should have received an email with that, but the schedule will be pretty similar. It's just that we are moving up some talks a little bit. So we have 4 talks tomorrow. That will be the last day of TWSS. We will not have any evening presentations. And those talks are actually going to be 8:30 and then 10, 11, and 12. So please make a note of that if you're looking to join us tomorrow. All right, any further questions before we take a brief break before our last and final talk of the day? Okay. All right, well, thank you so much, Daniel, yet again. You did a great job. It's always good to see what you've been working on, especially the stuff that I don't encounter as much when it's not just your work with clients. So it's always good to see, the other half of what you do as well.
Yeah, you're welcome. Yep, you're welcome.
Okay. All right, everyone, we will be taking a brief break. We will be coming back at 7 o'clock Mountain Time, so about 30 minutes. Our next talk that's coming up is actually going to be David Smith, one of a research scientist here, and he's going to be talking about using VSim to model terahertz microstructures in plasmonics. So please join us in about 30 minutes. Thanks so much, everyone. We'll see you in a bit.
Okay, bye, everyone.